Okay, so today's objectives, we're going to exploit Newton's first, second, and third law, particularly his second law. We're going to use free body diagrams to solve problems. Recall our general form of Newton's law, F net equals ma. This is, again, just our general expression. In component form, because we have to add things only in components, we have F net equals ma just expressed in three terms: the x direction, the y direction, and the z direction. And remember that we're kind of ignoring Newton's first law. And by ignoring, I mean we're saying it's a special case of Newton's second law. When acceleration is equal to 0, we know the net force is equal to 0. So we're going to start with this example problem. The example problem here, we have a curling stone, and we have two different forces acting on that stone. We have F1 at 10 newtons, 200 degrees, 210 degrees from the horizontal. F2 is just perpendicular from the horizontal at 20 degrees. We need to find F3 that gives our curling stone our acceleration. So here I drew a quick sketch. Our sketches include my coordinate system. Here's my stone, the acceleration I threw on there, F2, F1, and I have phi and theta respective. From there I drew a free body diagram. Now notice in my free body diagram, I don't have F3. I don't know where F3 is. I can't include it. I've also included the acceleration just to show the direction that it's going. I'm looking for F3. Next thing we're doing is adding that component diagram. Remember, we can only add things in like components. X directions with X directions, Y directions, etc. So I know F2 is a perfect Y direction vector. I know F1 is made up of two components. That's the x direction and the y direction, respectively. So once I have this component diagram, I'm going to start to apply Newton's second law. I know F net equals ma. My net force from my given information, F1 plus F2 plus F3, equals the total mass times the total acceleration. Our problem asks us to solve for F3, so I know F3 in a general form is ma, my mass times my acceleration, minus my two forces, just simplifying, minus F1 minus F2. From here, I need to get things into components so I can solve for my vector F3 in both component form and in that magnitude and direction form. So what we do is we're going to break things into components from my free body diagram. I labeled in my sketch angle theta. I'm going to relabel into my component diagram, I should say, angle theta. So I know my x component of force 1 is negative F1 in the negative direction, times the cosine of my angle, cosine theta in newtons. Same thing, Fy is a negative direction, negative F1, sine of the angle also in newtons. Same thing I'm doing now for F2. F2 has no x component and is a perfect y component. Now, because my expression has acceleration, I need to also break the acceleration into component form. Remember, acceleration is a vector just like force. So I break my acceleration into an x and y component based on the angle phi that they gave me in the problem. So I know my x component is a cosine of phi. I know my y component is a times the sine of phi. Finally, I'm going to apply vector addition. In the x direction first, F3x equals mass times acceleration. There's my mass. Here's my acceleration component of the x direction, minus my force component in the x direction, minus my force component in the y direction. That should say y. When I plug all my numbers in, I get an x component of 12.52 newtons. Same exact concept for the y. Fy is mass times the acceleration. There's my mass times my y component of acceleration, minus F1 sine theta. That's my y component of force 1, minus my y component of force 2. When I plug that in, I get a y component of negative 10.4 newtons. So in component form, F3 is equal to 12.52I minus 10.4 newtons in the j hat. If I go back to my diagram here, now if I wanted to, I can add that in. I know my vector is 12.5 in the x direction, comes down into the y direction. So my F3 should be somewhere in that vicinity. Now, in order to figure out my magnitude and direction, magnitude, I'm just taking the square root. This is just the Pythagorean theorem. 12.52 squared plus 10.4 squared. I get a magnitude of F3 to be 16.27 or 16.3 newtons. Then to find the angle, it's just right triangle trig. The inverse tan of y over x, we get approximately, it comes out to a little more or a little less than 40, I think it's 39.7, or negative 40 degrees, which would be from my x component, negative 40 degrees, or the contrary, 320 degrees from my horizontal axis. So I would report that answer as 16.27 newtons at 320 degrees from the x-axis. So for problem number 2, we're talking about an Atwood machine. I have a diagram up here, block S, which I've labeled as big M, block H, where I've labeled as little m, and in this problem, block H is falling. The things that I want to find here, I want to find the acceleration of block S, acceleration of block H, and the tension that connects the two ropes. In order to do this is a little bit more complicated. We need to identify first all of our forces. So I've identified 5 forces that I can see easily on the diagram. I know that I have a force pulling block H down. I know I have a force pulling block S down. Both of those forces are the force due to gravity, or the force of this block, and that other mass being the Earth. We talked about that today. Next, I have the force pushing block S up, which we know is the normal force. Finally, I have the rope pulling block S to the right, but I also have the rope pulling block H up. That force and that force are my tension force. And remember, this is an exploitation of Newton's third law. Those forces have to be equal and opposite. In order to solve for this problem, we need to apply Newton's second law to both objects. We don't do it simultaneously. We apply Newton's second law to each object individually, then combine all of our terms. So the first thing I did was choose block S. Here I have my components, and I'm going to use that component for both cases, though that's not always the case. So I have my components. I know I have a normal force going up. I know I have a force due to gravity going down. And I have my tension. Those are my 3 forces. As I look at block H, I have my tension. I also have my force due to gravity. 1, 2, 3, 4, 5. I ID'd and used all of my forces. Next, I'm still sticking with block S. I'm going to apply Newton's second law. In the y direction, I have the normal force minus my force due to gravity. And I know it's minus because those are the coordinates that I defined. Equals 0. I have no acceleration of block S in the y direction. That means I know the normal force is equal to the force due to gravity, which is just big M times G. In the x direction, I have again F net equals ma. I have my F net is my tension equals, I know this block is accelerating, big mass times acceleration in the x direction. At that point, I'm done in this direction. Next, I'm moving to the y direction. I'm sorry, not to the y direction, to block H. Block H, I have 0 components in the x direction. I also know that everything is just in the y direction. I have my tension component here, subtracting out my force due to gravity, and I know that's falling. So F net, tension minus my force due to gravity, mass times gravity, equals, little m is falling, times the acceleration. Now notice I don't have an AY here, but I do have an AX there. Our 2 blocks are connected, which means when this block accelerates, that block accelerates at the same rate, which means this AX is actually just my acceleration. We also know that, again, because of Newton's third law, tension and tension have to be the same. So once I have my, my equations, I can sub one in terms of the other. So here I'm subbing big M times A in for tension. So I have mass times acceleration minus the rest, mg, equals a negative ma. All I'm doing now is rearranging to solve for acceleration. So I know the acceleration of block S and the acceleration of block H in general form is big M minus little m divided by mg. Last, I can take my acceleration, introduce it into any expression that has tension, because accelerations are the same, to solve for tension. So I obviously chose the simplest form. So I got tension is equal to big M times the quantity, m minus m, divided by mg.